So, why is this thing freezing? Yeah. Today we'll be looking at sample size determination. I won't be able to finish it today, at least I will be able to read somewhere. Of course, we know that the major reason many people call statistician, even many people call me, you will think maybe they will call me because of that analysis. If people call me 10 times this week, none of the time it be for data analysis. Most of the time it will be for sample size determination. Sometimes the second reason is that, oh, I'm doing this type of study. Which type of statistical analysis will I do? But the most important, the most common, or the commonest reason is for sample size determination. But the second one is a type of statistic they will use. It's not that if you want to analyze, to write in the proposal. Then the third is, okay, I want to analyze my data. So sample size is very, very important. And I think it's timely. One of our guys here asked for it that you should discuss it and also talk about the practical way of using software. We will go to later, not today, we'll talk about how you demonstrate how you use WinPepi to even do some of the sample size determination, calculation rather. So what is sample size? Sample size means the number of subjects required in a study so that the difference thought to be important can be detected as statistically significant at a level of type 1 error, if indeed they do exist. I think somebody's machine is making noise. Please mute yourself. Mute yourself, please. Mute yourself. So, or should I mute? Yes. If you have question, you can type the question so that when we finish, we attend to the question. You can, if you don't want people to see the question, you can type it to me directly, or when you type it, I will not make mention of your name. If you don't want people to, I will just read the question and answer. So if you have question, you can type it as we go on. Okay. You see, in this description, to some people, it may be confusing, but to people that are familiar with it, may not be. The reason for it being confusing to some people is because of some things, type 1 error, alpha. If somebody does not understand what type 1 error alpha means, it's going to be difficult. We will explain this a little as we go on. And that is why whenever we do workshop, statistical workshop, I will not talk about sample size if I want to talk about it until I've discussed introduction to inferential statistics. When we talk about statistical error, we talk about type 1, type 2 error, because there's no way you can completely understand what sample size is unless you understand the concept of type 1 error. And the only thing I want to still explain that, the only thing I just want to explain here now is the difference. For you to be able to detect the difference thought to be important. That difference thought you need to see. There are some subjective aspects of this sample size determination because there are some things we get from experience. And that is why sometimes if work cannot be done in a particular area, it may even be difficult for you to even calculate the sample size. But when most of people do the work, either they just use any sample they got, at least whatever the person published, the work now will serve as a stepping stone for others to be able to even calculate better sample size and do better job. And that is why knowledge, you don't know everything. Nobody can know everything in life. but you keep on improving, improving, improving. When somebody publish a work, that work, that work will serve as a stepping stone for other people, and even you that your work serve as stepping stone for other people. You can the other person's work also will serve as stepping stone for you to move ahead also. That is just how we know in part. So that is why when we disseminate knowledge, we learn from one another, and we also, as you learn, also help other people. People learn from you. So the fact I want us to quickly look at the fact about sample size. One thing about sample, the larger the sample size, the larger the variance, the larger the sample size required. What do we mean by variance? Variance means the variability, the attribute, for you to detect the difference. If the variability is much, for you to detect the difference, the real difference, your sample size will be more. For example, if you want to understand what the variability means, what do you mean? Measure of variability, we know that when we talk about standard deviation, um, variance, that is how wide apart the attribute is in the population, the variability. We are not talking of the difference between two groups now. Naturally, how far apart is the attribute? And one way of knowing all the standard error, if the standard error is small, that shows that the attribute is not far apart. If it's standard error. So, but let's just leave that. Sometimes also, if you look at your prevalence, if the prevalence is close to the middle, if you put the prevalence over 100, if the prevalence is close to the middle, around 50-50, that's the highest variability, 50. So if something, an attribute is 50%, the variability is higher than the attribute that is 30%. It's higher than 40, it's higher than 60%, it's higher than 70%. Can you see? Maybe we'll demonstrate that later. To have considerable confidence that the difference thought to be shown in the study is real, the analysis must produce a small type 1 error, that is p-value. It must produce. If it is when your type 1 error is very small that you have more confidence, of course everybody understands that. Then if the investigator wanted to detect with confidence a very small difference between mean value or proportion of two groups, larger sample size. So it may sound conflicting. We have already said that the higher the variability, the higher the sample size you need. So also, the smaller the difference between two groups you are detecting, the larger the sample size. You're going to see, you will see that those two attributes I just said contribute. When you see the formula for sample size, you see the variability is numerator, and the higher the numerator, the higher what you are calculating, and the difference is denominator. The smaller the denominator, the higher what you are getting. So you will see. So for variability now, the measure of variability, if it's higher, you need higher sample size. When the difference between two groups, those difference between two groups serve as denominator. When the difference is small, you need larger sample size. Now, what are factors that determine appropriate sample size? That is, those factors is what you're going to be seeing in the formula, because the formula is not the real situation, but it's model life situation. So it is this thing that the intelligent people now put in formula to say, okay, let's just gather all these factors that determine your sample, what your sample size should be, and now put how are they related, what is the relationship, and now put them. So this one should be denominator, this one should be numerator. That's all. And we're going to explain them. There are 5 of them here. Minimum expected difference, estimated measurement variability, I talked about it, statistical power, significant criteria, that one is talking about your type 1 error rate. Yes, type 1 error rate. Then whether your study is 2T or 1T analysis. Those are the factors that determine what your sample will be. Now, the minimum expected difference. is the smallest measure, smallest measure difference between comparison group that the investigator would like to study the study to detect. The smallest difference. So there are some differences that are very, if it's too small, you say, oh, no, 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 I don't even expect this them to differ. No, if the difference is as small as this, I will not expect that both of them are the two groups are different. That's what it means. But once the difference is above or at least, is it at least or at most this different, at most, you will okay, that shows that there is a difference between. So the smallest or minimum expected difference. How do we get it? You will be surprised that some of them will be subjected to a certain extent based on the experience. How do you get it? Clinical judgment. So we are talking in the context of epidemiological study now. So if you are to be in engineering field, it has to be their own engineering judgment, their own experience, or the expert opinion. Therefore, we in the medical line is the clinical judgment. Then experience with the problem. Yes, sometimes there are some things, even when the difference is much, it doesn't make any difference in the outcome of the patient or in the result you expect. But there are some little difference that, they make is, the big difference. Just like there are some variables we make clinical um, signs or vital or most of our vital signs. There are some things. If you see that if the variation is much, even with little variation, some things that is signal unfavorable condition. Why some there are some changes that are still expected. So it depends on the clinical judgment, the experience of the person, the sort of pilot study. Can you see now? So sometimes that is why many people, sometimes some experts, the study, first time they do the study, they didn't calculate sample size. They just use their, it's not only because of the field that they experience. Sometimes the phenomenon they are studying or the variable they are studying may not even be common. If it's not common, they make use of what is available, especially if you want to do case control study. It's difficult to get cases in some situations. It's not a common condition. So whatever you get, make use of it. So that in that case, what samples are you talking about? So maybe you may now begin to talk about sample size for the control. And that is why in case control, it is allowed to even have to double, to triple, or even tetraple. But of course, it is advised not to go more than tetraple because somehow it will affect the result. The reason they allow that is because they are small, the sample size is very small. The cases you're able to get are very few. And for you to be able to test out the factor, for your analysis to be robust, you need large, minimum a large number. So that's why you now the control, since they don't have the disease, you can really recruit as many as possible. So the sort of pilot study can help in a situation where you cannot, that maybe the work has not been done before. You can do a mini fraction of it. That is, use smaller sample, just use of the subject or participant. Then use them to then do the analysis and see the result. In that case, to give you a clue about what they estimate, they still not the correct estimate, but it will guide you about what your sample size will be, because you're going to use the result to fit into the formula to calculate your sample size. Then literature review, and that is the commonest source, especially if much work has been done about the attribute, the variable you are studying. If much work has been done, you see literature. And sometimes also you will be looking for literature around in your ecological area, because sometimes there are some attributes that vary across the globe based on your location. So because of that, people will prefer studying in their own continent, or if not in the country. When the situation you cannot find, you can see you use literature review from anywhere. There are some situations even from anywhere you may find difficult to find, because if not much has been done in that area. Whichever way, if you look at it, if there's literature there, you use it. If you cannot use, can use philosophy. If you cannot use that, you can use clinical judgment, experience with the problem to calculate, to estimate what your sample will be. So together, minimum expected difference. But still go by when you get to the formula, I will tell you what that minimum expected difference just means. Very simple. The estimated measurement variability talk about how vary, how far apart are the attributes of the population. For example, now you know that everybody knows that if you compare height and weight, you know height vary more in less in the population than weight. Weight vary more. That is very weight vary more among people than height. You see people, you gather people, they may not differ much in height, but they differ very much in weight. So I weight. So when you talk about variability, you talk about how naturally how this thing vary on the population. And sources of estimated measurement variability, preliminary data collected from similar studies, population, just like what we said, that's literally, then apart from that, literature review. So even the preliminary data you may not, they may not even, maybe they have not published, but you have access to the data. So you can use it to calculate the your estimated measurement variability, then literature review, subjective experience. So it's just like the clinical judgment also for minimum expected difference. Assumption, just assume. I'll give you an example. Many a time, if people are looking for prevalence of attribute or an attribute, the previous work to be able to calculate your sample size for descriptive study, even for analytical study, I think you discover that sometimes you cannot find. You can assume. But the assumption also, most of the time, it's not as if, in fact, the assumption also will even give your work more power. More power when you assume. Most of us are familiar with maximum variability assume. You choose 50%. And as I went off, I'm in one village in Nasarawa. I'm very sorry. Just went off. So, resume. Yeah. So, you choose 50%. 50%, I said before, is maximum variability than 60%, than 40%. We'll demonstrate that later. Now, estimate, okay, let's statistical power. You know, the statistical power is ability that a test or a study will indicate a difference when the truth is one. That is, if the difference is there, your ability to get it. If the difference may not be there, but if the difference is there, your ability to detect. If the difference may be there, your study may not get it. And that is the power is not powerful enough. And that is why if you will not say that you accept no hypothesis if you cannot find a difference. You will not say I accept no hypothesis, there is no difference. You just say okay, you fail to reject in the sense that oh in this study I cannot find a difference. It doesn't mean that difference does not exist. I cannot find it, but it doesn't mean it may be that your work is not powerful enough. So if the difference is there and your work is able to get it, that is the power. That shows that your work is powerful. Now, the degree to which you are able to get the difference is there is the power. It's increased as sample size increases. You know, you can state this statement in two ways. Both of them will be correct. As power increase, sample size increases. As sample size increases, power increases. So you will begin to know, if you have high sample size, you will declare the difference. That shows that as the sample size increases, power increase. But as power increase or sample size increase, you can determine your power from the outset. And so, okay, my power will be 90. So you have factor it is we bring some condition into your work so that you'll be able to decide. So you can determine your power. So if you see your power is going to be 90 compared with someone that says the power is 80, you will require for that particular thing other things to be equal. You require more higher sample size than the person that shows power of 80. Customarily set at 0.8, which is 80%. They can, people experts are advocating 90%. Then the standard normal deviate that corresponds with the selected power. Though here now he's talking of the probability now. The power is 80. 80%, that probability that you detect the difference is 80. But what you've put into your calculation is not actually that power. It is this corresponding with that power, which is the standard number. That is, if you use normal distribution, standard normal distribution as a template, the probability that you detect the difference is 80, that's your power. The probability that you not detect is somebody is raising hand. Is it that you cannot? Oh, hope is not that because you were logo. I'm not muted. I'm not muted. Somebody is raising hand. Yes. Somebody raise hand. Any question? Any question? Somebody is raising hand. Okay, maybe the person just raised hand for fun. Okay, let's continue. So when we finish, you will ask question. Right. It's like, can somebody hear me? Can you hear me?
Yes, we are
Yeah.
hearing you, but we are
Yes,
not seeing
yes.
the slide. The
Okay.
slide again.
Okay, don't
Yes,
worry.
we're hearing.
Don't worry. It's like the network. Don't worry, it will come. It's like it's the network. Just a minute. I'm in one village in Nasarawa State, so it's the network. Let me just correct it. Why is this thing not coming? Well, I don't know. It's the thing. Just a minute. Yes, just a minute. So I have to. Okay, I think I've not reached this place. Yes. So you can see the slide. I don't know. So the power is. Sorry. I'm back now.
Okay.
Yeah. So the power. So the if you use normal distribution, standard normal distribution, so the larger part of it is the power, that's 80%. That's probability that you get the difference. The smaller part of it is 20%. So the in between, the along the horizontal, in between is the standard normal disease score that corresponds with that point. That is what you are going to use, not the probability set. Yes. And this is the table, standard number deviation that corresponds with the power, statistical power. And initially one thing, that's one thing with power. Is one side. When you draw your normal distribution, it's one side of it. And I didn't demonstrate it here. Maybe in the next time, 2 days time, we further our discussion, I will show it. If you can see now the 80, the power of 80, the standard normal deviation that corresponds with the power of 80 is 0.84, and that is why the Z score, the Z score, the Z that corresponds with it is 0.84. For 19 is 1.28. So those are the, if you are using power of 80, you use 0.84. That's what you substitute for that Z. That's what you see in your, as you see the formula. Then for 19, you use 1.28. So you can use 85, but people don't just use it. It's only that if you cannot use below 80, people will criticize your work. But you can, there's nothing that ties somebody down to 90. You can use 85. You can use 95 if you want to use. The only thing is that we can't call your sample size. So there's nothing, you don't have anything to lose by using anything greater than 80. This slide not changing. Okay. Yes. Significant criterion. Yeah, now we just talk about the power. Significant criterion is close to that also. It's the Z-score also. It has to do with your type 1 error. At what p-value you say that you go to reject null hypothesis is customarily set at 0.05. And this one now, it depends. It can be 1T or 2T, but the power is always 1T. But this one can be 1T or 2T. If it, whatever, this may if you set it as 0.05, the corresponding Z is, if it is 2T, is going to be 1.96. Look at it. 2T is going to be 1.96. If it's going to be 1T, just double the significant criteria. 1T, look at it, it's 1.65 or 64, 65, 1.65. So you will see that well, with 1T, the Z is smaller. And that is why, even when you are running analysis or you do study, your study is 1T, it is easily significant than 2T. Now, when we see the formula, all those things we feel, yeah, what does it mean to say 1T or 2T? 1T or 2T just have to do with the way you set your hypothesis. If the difference you are looking at between two groups is just a difference, it doesn't really matter if A, that attribute is higher in A than B or B than A. Just like if you are studying something, prevalence of anemia among under 5, rural and urban. It doesn't really matter that the anemia is higher among rural or higher among urban. You want to see if there is any significantly difference in anemia between rural and urban. So you are not testing whether urban, the anemia will be significantly higher in rural. So it's 2T. Anyone can be higher, anyone can be lower. But if it is 1T, you already made up your mind, or you feel that it makes only one sense in one direction, that you know that, or maybe you have established that anemia is higher in rural, but you just want to see the difference between rural and urban is statistically significant. So in that case, your hypothesis is anemia in rural significantly higher than that of urban. Is this significantly higher than that of urban? That is what 1T means. So 1T is unidirectional, and there are a few cases that it makes sense like that. I've forgotten some examples which I've encountered before, but I just fabricate one. Whenever I take my class, I just fabricated one. The example I use to differentiate 1T and 2T, the example of 1T I give is, imagine you have some women attending antenatal and their first daughter also attending antenatal with them. The first daughter are pregnant also. In that case, there are some women that marry very early. When their first daughter starts even giving birth, they are still giving birth. So in that case, if you now say, okay, you want to see the average age of mothers and the daughters, if there's any significant difference. In that case, it doesn't make sense to even talk about 2T, because if you calculate averagely, there's no way daughters will be the average age of daughter will be higher than that of their mother. It's not possible. The only thing you may not see much difference, and if that difference you want to see is significant. This difference, we know that mother are averagely higher, older than the children. That difference you observe is statistically significant. They are much different. In that case, that is one thing. One thing. Well, you know that the result can only be in one direction. That's just an example. Then computation of sample size. Now, for you to compute sample size, the type, the approach, the formula, whatever, depends on study design. The type of study you are looking at, the number of groups being studied, the outcome variable. Those are the factors that come to play. So if you look at study design, this is just a epidemiological classification, simple classification. I also have alternative classification in the next slide. This simple classification is just okay. That's what many people are familiar with, and it's easier for people to conceptualize. But it doesn't really mean that it makes the best sense, statistical sense. The alternative classification actually make more better for statisticians. It's the same thing when you classify variable into quantitative and qualitative. It is easier, but it doesn't make uh, statistical sense as classifying them as ab initio as discrete and continuous. Now you see, in this case now, epidemiological study, experimental. You know that when you intervene, then observational. When there's no intervention, the observational, if you see the experimental, you can have two groups, you can have, what do I call it? Either the two groups, there's randomization or not, then you have two groups because the statistic is not interested, does not even know whether it's experimental anyway. As by experimental in the sense that you intervene. The statist doesn't know, maybe you give integration or whatever you the intervention you did. What is saying is you have comparison group, and one thing by nature, experimental design has comparison. There's no experimental design without comparison group. Even though when we say group, doesn't really mean that it has to be group of subject. We are talking of the group of observation you carry out, the group of data. So when you say independent group, mean that these two groups or three groups of data are from independent, separate group of subjects. If you say dependent group or peer group, or what you call before and after, these two groups or even three groups of observation or data are from the same people. But the issue is that whether they are from the same or different people, that you cannot, yes, there's no experimental design with just one data set. No, it's not possible. There's no experimental, that is one nature. By nature, experimental design it has comparison. It's come with comparison. What the statistician is interested in is not whether we perform experiment, but what he's interested in is these two groups of experimental data you collect, are they from the same group or are they from independent group? That's the interest. So when you come to the observation side, you know that when you say descriptive, you are talking of only one group. When you now say analytical, there is comparison group. There's comparison. So you see, by nature, if we have descriptive analytical means there's a comparison group. That shows that by nature, experimental design is analytical. So if you, that's the alternative clarification, experimental design is analytical also. So there's an overlap. So what we want you to see here is, are you dealing with one group or two group or three group? Those two group or three group, that is when you have more than one group, are they independent from independent subject or they are from, is repeated, they're from the same group. That's what statistics is all about. And that is what sample size also recognizes. Now, the alternative classification of study design, say descriptive analytical. Of course, you know that under the analytical, you can have observational and experimental. And of course, whichever way you do it, there will be overlap because the observation also is a form of descriptive study. Is a, what do I call it? It's a descriptive study, rather, it's a form of observational study. So that's another, but this one, I will tell you that this one gives more statistical sense because this was a descriptive one group analytical comparison, and that is what computer statistic recognize. No, that is, are you dealing with one group or you have comparison group? If there's comparison group, he's not interested whether it's experimental or observational. Is it independent or dependent? That's what statistics is all. And the sample size also. The mode of computation now, you can apply the formula manually or use software. The software also is just, instead of you calculating manually, they have already calculated. It's not as if maybe calculated. They already computed the sample size. Means putting all those factors together. Now, if you want to calculate sample size for descriptive study, from here now, from what we discussed, we now talk about one group. Here we are talking of one group. And you remember I said another factor is not only the group. Another factor, I said it earlier, is number, the outcome variable. Apart from the group, number of group, the outcome variable. Is it summarized? Is it categorical or continuous or numerical? Let's say numerical. The outcome variable. So when you are dealing with a categorical, you summarize categorical with proportion. When you say you are comparing estimating proportion. You know, in this case now, when you are talking of one group study, you are not comparing two groups, but you are estimating. Though estimating is a form where you are comparing what you have with what is in the population. But you are not comparing two groups, two samples. You are comparing only one sample with the population. You are estimating, you are trying to estimate the population parameter. You see what you get in your sample. Is it the same thing with what? Or you are trying to estimate this because you cannot actually even know if it's the same thing. The only thing is that you just want to be as close as possible to the population parameter. Now, the meaning, look at the formula, look at, we use the first one on the left side, estimating proportion, on the right side, estimating mean. If you look at their similarity in the formula, the only thing, what are the similarity? Is this, the Z, which is the standard normal deviation that corresponds with the level of significance. Already said, if you set the level of significance to be 5%, that shows that your level of confidence is 95. You know the level of significance, level of confidence add up to 100. So the standard normal deviation, the standard deviation that corresponds to that is 1.96, and we discuss it. If we discuss it when we're talking about is it the normal distribution under when we're talking about probability and normal distribution. We have already established that in normal distribution, the middle between -1 and +1 standard deviation, 60% of the observation line. Between -2 and +2, 95.74 or 45% line. But the researchers, they are not interested in the middle 95 points anything. They are interested in the middle 95 sharp. In that case, it cannot be up to the 2 standard deviation. So when you remove the difference, it's just small. So that is why it's 1.96. So the middle 1.96, the middle 95% of is in between -1.96 standard deviation and +1.9, and that is what we are calling standard normal deviation here. So the standard normal is Z, 1.96. If you choose 5% as level of significance, if you look at the one that corresponds with 0.05, that is, if your level of significance is 0.05, look at it, it's 2.57 to approximately 2.58. That is your, if you are choosing the levels, your significant level is 0.01. That will choose 2.58 as your Z to calculate. Of course, you see that thing is numerator. So if you increase your numerator, it will jack up the sample size. And so if you want to increase your level, people are having problem with network. Where is this place? Not easy. So what you do, you can see that the Z is the same on both sides. On both sides, either you are estimating mean or estimating proportion. It's the same. What differ here? P, you can see P because you are dealing with prevalence here, proportion. Also finished. Oh, I'm very sorry. Please. Yes. So whether you are dealing with, you can see. Just a minute. Hope you didn't pause the. Okay, it didn't pause. Okay, let's just quickly finish because I don't know what's almost true. So we can ask our question. So you will see here what I wanted to show you the note here. You will see here that Z and Z the same. Okay, the only thing I forgot to show you. Somebody, I have to unmute you here. So the only thing I didn't put here is missing is Q. The Q is 1 minus P. The Q is 1 minus P. That's PE, that's Q here. Is 1 minus P. But when you now come here, what you have instead is the standard deviation. S is standard deviation. If you say S squared, you can just call it variance. The standard deviation, S is standard deviation Of course, here you are dealing with quantitative variable. In the quantitative variable, if you summarize, you say mean and standard deviation. So you don't have proportion, it's not summarized as proportion. So this is standard deviation. Now when you come here, what is the denominator? The denominator here, okay, this P is the prevalence of the attribute, the prevalence, the percentage. While S is standard deviation of the attribute. So this one is for categorical, this one is for quantitative. But here, what is D? D is the level of precision. If you look at it, D is the only one that is denominator here. It's the level of precision. It's called, you can, in fact, the best name for you to understand what it does is maximum error of estimate. Yes, it measures precision. How does it measure precision? Because you are estimating population parameter. You don't want to deviate from population parameter. You don't want what you're going to get in your sample to deviate by more than certain percent. And people usually choose something like 5%, which is 0.05. That is level. That is, if somebody chooses 5%, another person chooses 2%. You see that 2%, the person doesn't want to, will not deviate from the parameter more than 2%. It's more precise than 5%. So that is why the layer is measure of precision. But the name that fits it most is maximum error of estimate. That is error you want to that is you don't want to go beyond that error, maximum error. You know that because you have not taken the whole population, you can never get the parameter. It's not possible unless you take the whole population. But you don't want to deviate. You don't want your error to be more than a certain percentage. And that is that value 0.05 that you usually should. That 0.05 is different from the level of significance. What corresponds with the level of significance? Your 0.05 level of significance is the Z, because it's the one that corresponds with standard normal degree 1.96. So what represents your 0.05 level of significance is 1.96 you put for Z. But this is 5% they usually put 0.055 usually put down is not representing level of significance. It's representing maximum error of estimate or your level of precision. Then when you come to this side, you see it look funny, but it's the same thing. It's still the same maximum error of estimate. But to be able to conceptualize it, is it acceptable error or change in the mean? Because what you have here is standard deviation. What you have at denominator will be mean. Oh my God. This, hello?
Yeah, we can hear.
Yeah, I don't know. This network is just, let's just quickly finish. Just messing up. Yes. You see here that this E, acceptable error or change, is the mean, that is how, what is the difference in mean? You want your own mean to differ from the population value. It's not the mean you put here. If you don't want it to differ by more than 5%, you now calculate 5% of that mean. So in your literature, when you say, okay, you get the mean and standard deviation, you use the standard deviation as the numerator, but you now use 5%. If the 5% you want to choose, you now should choose 5% of the mean as the E. Because if you don't do that, you enter into a problem. Two-way problem. Any of them is possible. You know, the standard deviation you put here is not standardized as per the standard deviation of height. When you talk about it, depends on the unit. Like height now, we measure in 1 point something in meter, is 1.7 something, and maybe the standard deviation will be 0 point something. Then when you look at weight, you'll be talking of mean 80 something, 70 something, and the standard deviation maybe 20 or 15 kg. So in that case, how do you reconcile? You cannot compare the two. So in that case, you cannot go and put just 5%, because that why we use 5% here is that the numerator for this side is already standardized because it's measured in percentage also. The prevalence is measured in percentage. The error, level of error, the maximum error is measured in percentage. Even though you change it to a decimal, by just divided by 100. If you decide to put that P, I express it as 100 and Q as 100, then D will be 100. It will give you the same answer. So it's already standardized because the numerator and the denominator, they are in percentage. But if you use mean of that attribute and you now come and put D as percentage, what will happen is that if that particular attribute, the mean naturally due to the scale is very small, like something like height, what will happen is that because it's the numerator, in fact, some people calculate sample size less 0 point something or 1 because of that. In another way, if you what you are dealing with is something that maybe you are dealing with new kilometer distance travel, when you are talking of 1,700 kilometer, then plus or minus 150 kilometer or something, plus or minus 80 something kilometer. So if you go and use that type of thing, what may happen is that you may have very big value. So because you have not synchronized your numerator and denominator. For you to what the only thing that can make you to synchronize it when you use the standard deviation, you now use the percentage, you now calculate your error from the mean. If your level of precision, you want it to be 5%, calculate 5% of the mean and now put it. So it will cancel each other as per the unit. Because the unit of the standard deviation is the same thing as the unit of the mean you use. Now, the alternative to that, if you don't want to do that, is using this formula also, the way it is. That's what I put down. But when you use this formula, but your D is not just your D, your P is not just the prevalent, because of course you cannot calculate prevalence here because what you have is mean and standard deviation. Your P will now be this coefficient of variation. Coefficient of variation is standard deviation over mean. That is what you just do is to cancel out the unit. The unit in that is that unit that's causing problem. When you cancel, you divide the mean, the standard deviation by the mean of the same attribute. It will cancel out the unit out. In that case, you can express it as percentage. So we call it coefficient of variation. That is the only way you can even compare variability between different variables. Like now, if you want to compare variability in weight and height, there's no basis for it because the measure of variability, which is standard deviation and variance, the value when it comes to the figure is very big when it comes to height, weight. Compare with height, if you measure height in meter, they compare with kilometer. When you are measuring, we are talking of something 100 kilometers. So in that case, when you do your coefficient determination, it allows for comparison of variability between two different variables. So when you put it here, you express as 100 is like P, prevalent. It will now be serving like prevalent, and you can calculate your Q by removing it from 100 or from 1. For you to say you are removed from 1, that should that you didn't express as percentage. You don't express as percentage, you are talking of 1. 1 and 100 mean the same. 1 is 100 expressed as percentage, while 100 is 1 expressed as a fraction. Now, I think that one is very clear. So if you do that, the drawback of this one is that sometimes if the work has been done, the standard deviation is extremely high. Maybe sometimes standard deviation can be higher than the mean. There's extremely skewed data. If you encounter that, you have problem calculate it. But these are the two options you can have to calculate your sample size when your estimate, your outcome measure is quantitative. Many people try to overcome that or dodge it when it is easy for them to convert their quantitative variable to categorical. For example, instead of you talking about the mean blood pressure, now talking about prevalence of hypertension, you just go and have cutoff. How many hypertensive? Instead of you to talk about mean hemoglobin concentration, you talk about prevalence of anemia. No, you just look for cutoff. But sometimes when you have cutoff, when you're comparing groups, when you just do that, you lose a lot of information by categorizing quantitative variable you lose a lot of information. So it may even make sense for you to compare groups based on their raw data and use appropriate statistical tests to compare them than just categorizing. So instead of you trying to compare them using the mean, you now say, okay, let me go and compare them using the proportion. Now, you can still make, we are just talking about estimate sample size for descriptive studies, whether the first one is categorical outcome, the second one is quantitative outcome. But even with that, you still have, is anybody having issue with hearing me? You cannot hear me? So now, you need to adjust for finite population. What do I mean by finite population? This one we just did is assume that the population you are studying is infinite. Well, infinite, there is no sharp boundary between finite and finite, but infinite. But when we calculate sample size, experts use 10,000. Any population that is 10,000 above is believed to be a large population. We can call it infinite. But any population less than 10,000 are small population. Most of the time, as clinician or health professional, we try to study in facility, study people that come to particular facilities. In a particular facility, you see that the population you are studying per time may not even up to 10,000. Maybe those people that have a particular come to a clinic over a year, over 6 months, over 3 months, over 1 month, it may not be up to 10,000. So in that case, this one is just to adjust. How do you adjust? After you must have calculated with that one, you now bring that n. NF means the final one. You want to calculate with that n over 1 plus n over n. This capital N is the study population. That is in the clinic. How many people come to that clinic within that time you are going to do your study? You may not know it unless you even look at the record. To look at in the last 1 year, you believing that it's the same flow. So you use the record to estimate. So if your work is going to be over, you're going to collect your data over 1 year. That shows that you use 1 year as estimate. If it is 6 months, you divide 1 year estimate into 2. If it is 3 months, you divide into 4. If it is 1 month, you divide your estimate 1 year estimate into 12. That is just the logic. So when you do that, you now have your capital N, that's the population you are studying. So you now put in what you have calculated before is n over 1 plus n. If you look at it, you remember Goldman, if you want to solve this, you have to first of all put this small n over capital N and do that. You now add it to 1 before you divide it. Because this n is not all over 1 alone. It's all over 1 plus n plus over n. So you have to first of all calculate n over n, then you now add to 1 before you now divide by this n. You now see that it will now reduce your sample size. If you don't do that, there are some situations you calculate your sample size based on the first set of equation. You now discover that the sample size is even more number than the population you are studying. People that come to clinic within that time. What will you do? So you need to adjust. That's the way to adjust. The only thing I've not put here, maybe we'll be discussing that by the next lecture, is the attrition. We discuss that. How do you? Many people just say, okay, if they just 10% attrition, then you just, if they have calculated 300, they add that 30. It's wrong. Because if you calculate 300, you add 30 as 10%, that's 330. But if I ask you to calculate 10% of 330, when you remove it, the remaining will be less than 300. Because the 10% of 330 is not 30. So we'll discuss that next tomorrow. I think we should stop here. So from next one, we'll now talk about analytical study. That is when you are now having comparison group, you look at the sample size determination. Okay, let's give room for questions now. So I think.
Thank you very much.
Yeah, you're welcome.